These problems are pretty straightforward. I'm sure you solved the problem like this in your physics class before you got here. So that's why I wanted to cover this simple problem. But it takes a little bit to refresh our memory. Determine the force required to hold the 300 kilogram mass in equilibrium. So this object right here has a mass of 300 kilogram. 300 kilogram. It has a weight of 300 kilogram force to be consistent, because a lot of us talk about kilos as a weight as well as a mass. And that's very consistent out there in the literature. Or you take 9.81 and you multiply it by 300 and you get how many? 2.943 kilonewton. Okay. So you're going to hold it by holding down this rope, pulling this rope down right here. And the first time you see these, I encourage you to go slow. What do we have? We have 3 pulleys, don't we? But the pulley has a pin through the middle of it that's often, this is like a little bar connected to that pin. That pulley can freely rotate about that pin. That's our analysis of the pulley. So that the tension in this cable that's being pulled down with a force P has the same tension as I go around the pulley. So let me do this. I'm going to color code it. And this is my first cable. It's a blue cable. It comes around the top. It comes down this side. It goes around another pulley. And it comes up and it stops at that block. And it connects to the bottom of the block, which is connected to the pin. That's one pulley. I tried to color code it blue. Let me try and color code the next cable red. The red cable comes up, goes around the pulley, comes down, goes around this pulley, comes up and connects to that block, that member, at that pin. And the next one, maybe I color code it green. It comes up, goes around, comes down, goes around, comes up, bing. So really, what do I have? I have 3 unique cables. Each of those 3 cables have different tensions in them. But anywhere in the blue cable, it has the same tension. Anywhere in the red cable, it's the same tension. And anywhere in the green cable, it's the same tension. There's just 3 tensions. So we could call this one, I don't know, tension in 1. We could call this one the tension in cable 2. And we could call this one the tension in cable 3. Okay. Now, you can pick many free body diagrams to analyze this problem. You could pick a free body diagram that comes in. I'll try and do it here. It's going to come in and cut around and go through, and so it's going to include the weight. It's going to include the body mass with the gravity. It's going to be going downward. That's the weight. And then we could come up and we can cut through that cable right there. And we could come up here and we could cut through all of those cables and then come down and close. Do you see that? That's a good free body diagram. Somebody says, I want a different free body diagram. I want you to include the weight, but when you come up, don't cut through that cable. Cut before you get up to that cable. Come all the way up, up, and maybe cut right through those 3 cables and come down. That's also a good one. It's just that now, not only do I have the weight as a load inside, I have the P inside pulling down. You could do multiple free body diagrams. I think I have an illustration right here trying to show you that you come up and cut through these cables and come around. Come up, cut through that cable, go outside, go out there, cut these cables, come around, come up, cut that cable, come up here, cut those cables, come around. All of these will work. You could come in and analyze this pulley A by itself. What do you mean, this pulley A by itself? Well, if I focus on the pulley A, I'm going to be pulling up in tension of cable 2. And then on this side and this side, as well as in the middle, I have the tension in 1, the tension in 1, the tension in 1, don't I? Because that was what color coded I have it before, I forget. But so you get that the tension in the second cable is 3 times the tension in the first cable. Likewise, you could do a free body diagram of pulley B. And when you do a free body diagram of pulley B, you get that the tension in this third cable pulling up is equal to 3 times the tension in the second cable pulling down. So there's a lot of ways to analyze this problem. We just have to pick one and be consistent. Let me see, what did I do here? All right, so what I did was I said that the tension here, the tension in 1 is equal to the load P applied. And then right here, the tension in 2 from the free body diagram member A is 3P. And then the tension in 3 is 3 times 3P, or 9P. And then whatever member I want to do, if I want to come like this, I can come up, I'll not cut through the cable, so the load is implied inside, and then come up, and I'm going to cut through those 3 and then down. That would be fine. So what I'll have is I'll have a free body diagram with 3 T3s up. I'll have a P down, and then the weight down, W down. Okay? And the 3 T3s is 3 times 9 P's, so that's 27 P's up. Get a little complicated, but that's my free body diagram. So when I do the sum of the forces in the Y, I'll get that must equal to 0. I have 27 load P up, that's the tension in the first cable, equal to 1 P down plus the weight. So I move it over, and I get P is W divided by 26. That makes sense? Okay. So when you calculate the weight, it's 300 kilograms. You divide it by 26, and you get that it's so many kilogram force or so many newtons. Why do I have a minus sign there? Isn't that an equal? The weight is 300 kilogram divided by 26, or 11.54 kilogram force. And then it's also multiplied by 9.81, you have 113 Newton. I encourage you to take a problem like this. Maybe I went a little fast, but I think you've solved these type of problems in the physics class before with a prereq. And there are multiple ways to solve it. It's just that you have to be consistent, okay? So be able to do free body diagrams around each pulley, as well as around a smaller section, a larger section, etc. I'll be in my office if you have any questions. Thank you for your attention.